I'm Christian Gscheidle. I'm a PhD student at the Technical University of Munich. And yeah, I want to give you a quick update today on permittivity sensors we are building for Planetary and also lunar exploration and the prospecting of water. So as a little bit of a background, we developed instruments to search for water in situ on the lunar surface, and wanted to look at how much water is there, and what state is it, and actually what's the vertical and also the horizontal distribution of it, and does it actually change over time? And yeah, we developed an instrument, the Lunar Volatile Scout. I have a picture of it later in the slides. And one of the problem was that it's a drill and it has an open end, and so have problem with constraining the initial abundance of volatiles in the regolith. And one approach was then to use the thermoelectric properties of the regolith to answer this question of the initial abundance. And so basically we just looked at such a very simple RC circuit, which you can see here on the slide, and used the regolith as our dielectric material for the capacitive element here. And so if we apply a potential to then our over the regolith, we get a distinct charging curve. And yeah, so hopefully we can measure how much water is in there and what state it is. And so we can do that on the surface and in a more or less non-destructive measurement. And yeah, so a little bit of a background on the electric permittivity for regolith and also for water, which is quite different. So we heard a lot about radar and other electromagnetic measurements, but we're not actually looking at the very high frequencies, but much more in those low frequencies where the water has a significantly higher dielectric electric permittivity than regolith, and the vacuum which we would expect to have in like this ternary mixture. The permittivity changes with density and also with porosity of our sample. The mixing laws, it's not very linear. So if you put more ice, less ice in it, it's not linear, and it also changes with temperature and with frequency. And we kind of use these properties to then hopefully detect water in the samples on the moon. And so maybe a little bit of the developments we're involved in is a prospect speed sensor. So here's like the mock-up of the drill rod from Proceed with our just for checking the CAD, we 3D printed the electrode assembly and fitted it in the rod, and so you can see it here in orange. And so this one's 40 centimeters from the drill tip, and so we're looking at the first 60 centimeters of the lunar soil, which we can investigate with the P sensor, and we can also do like a radial. So by just turning the drill, we can do a radial survey and also like this vertical survey. This was successfully tested by Philip, who's currently chairing the other session, and at ESA. And we're doing de-risking activities at TUM, and also gonna do the calibration then. So this is a little bit different. So these are the applications we're investigating right now. On the one hand side, our Lunar Volatile Scout, which I mentioned earlier, which has this drill shell and the heating rod, and this forms the two electrodes of our system. And if we drill it inside, then we can investigate the regolith between these two elements. Ideally, we would love to have a mass spec on top, so we outgas the regolith and look at how much the capacity changes from beginning to end of our measurements. And then the thermal extraction, there's this thermal aspect is quite relevant. On the other hand, if we just want to look at the electrical properties, we also investigating patch electrodes, like here. It's on the left hand of you, which you can basically apply to more or less, so quote unquote unused surfaces like a robo wheel or a land or footpath, and just measure how the soil is beneath these surfaces. These are flat electrodes, and we're looking at like flexible PCBs as sensor surfaces. Yeah. A little bit about our experimental setup. So we did currently it's a more or less commercial microcontroller controlling all the operation. We have this 12.5 hertz base frequency excitation, and then the ADCs on the back end. We did calibration with like just regular air, some plastics, some stones, and also sand. And this showed quite good correlation between what we measured and what we expected. We actually also did some experiment with JC1A with water in it and like over temperature, but here we will still have to do some analysis. And we're planning to have a dedicated TBAC facility for this and to do the experiments in there, so we have more representative results from this in the future, hopefully. Some basic results I want to show you here are how these curves look. So if you look at the curves down here, you can see that these are distinct for the different materials which we investigated, and also in the frequency spectrum. These peaks are very distinct, and there's quite a good signal to noise ratio between the background noise and our measurements, which are these multiples of the base frequency. And this is the calibration we performed, and so you can see that this was quite good. There's still some to be improved, I mean, but and you can see up here the noise levels get worse when we add a lot of water and change the temperature, but still the overall performance is still quite good. To further understand the whole system, we modeled it in COMSOL, and so we have this multiphysics COMSOL model with heat and mass transport, and also for the electric fields. And so just one snapshot for these transient analysis is like here at 10 minutes heating, and so we increase the temperature of the regolith sample, desorb the water, and so we change so the permittivity changes, and so the capacitance also changes. Same goes for these patch electrodes. So, but there we don't have a heater yet. We're looking at this, this basically behaves the same. Just a little technical context for such missions. So, what I find really beneficial and nice in this concept is that they're quite simple, actually. They don't require a lot of electronics or a lot of math, but they can give you significant scientific data back. So we hope to find more possibilities to fly such sensors in the future. So a little bit of conclusion for our instrument. My colleague took a nice picture here from the test campaign from the LoveMeX project. We think that this is a good way to constrain the water content on the moon, and possibly also on other bodies in the solar system. We can look at not only the water content, but also probably constrain like porosity of the soil and the electrical properties, so electric conductivity. We have a low system impact, and for our advancements, this is just further development And yeah, maybe two side notes, these two concepts, so the LVS and our permittivity sensors were recently selected for these reserve pool instruments, and this was quite exciting. And yeah, we're in the process of writing a paper. And yeah, if you're interested, hope it will be published soon. So that's about it. Thank you.
Thank you.